In this video, I am going to show how to represent the kinematic behavior of ABB robot, specifically ERV 140 robots, through multiple equations that allow to find the instantaneous position and orientation of each articulating body of this arm. So, I start by giving a short description about this system, with some specifications and geometrical features. Second, the forward kinematics is described to determine the movement of an effector with respect to angular displacement of each revolute joint. Third, opposite case is analyzed by inverse kinematics, where angular displacement of each joint is computed from position and orientation of an effector. In fourth, some simulations are developed to show the tracking of reference trajectories along the robot's workspace. And finally, final recommendations of this work are outlined. The IRV 140 robot of ABB Company is a compact industrial manipulator with 6 degrees of freedom and with a robust design so that it can be mounted in the floor, in a roof of embedded form, or in a wall at any angle, where flexibility, precision and velocity range are remanded into whichever robotic process. Besides, this robot is fairly useful for many applications and handles a considerable quantity of versions with an integrated coupling, which makes it suitable for places such as corrosive or foundry environment, but without varying its basic configuration of 6 rotational axes. Within the main applications, we have arc welding, assembly, cleaning or spraying, machine tending, material handling, packing, and deburring. The load capacity of this robot is 6 kg at the wrist scope of 810 mm, and now I show the robot's movement constraints in the following table, where the established working range and velocities on the 6 rotation axes are present. Then, robot's workspace is shown in the following figure, where previously mentioned applications can operate without restriction for the 6 degrees of freedom. Okay, forward kinematics has as objective to determine the position and orientation of robots and effector, or the gripper, either from the prior knowledge of angular or prismatic displacement along each robot joint. Then, for analyzed robot, it is required to know how is the pose of its end effector when each revolute joint is submitted to an angular displacement. It must be realized that this robot has 6 revolute or rotational joints to achieve a kinematic behavior of 6 degrees of freedom at the end effector. So, I present the analyzed ABB robot with a specific positioning named as home position. Under this configuration, I proceed to identify the bodies or links of this arm. First, I have a fixed body defined as the link 0, or the robot base. Then, the first mobile body located on the robot base is named as the first link, and successively, the second link is the given definition for the attached body to the first mobile link. The third link is the attached body to the second link. The attached body to the third link is defined as the fourth link. And finally, the attached body to the fourth one is defined as the fifth link. Given that robot has 6 rotational joints, I conveniently place 6 arbitrary reference points as the origins of the joint axes, whose locations are along to the longitudinal and vertical plane that makes symmetric the volume of the robot at home position. Thus, I present the joint Q1 attached to the link 0, and its rotation axis is defined by convention as Z0, whose origin is located where the blue arrow starts. Posteriorly, the joint Q2 attached to the link 1 appears with its rotation axis Z1, whose origin was located at a vertical distance L sub 0 and horizontal distance L sub 2 from the origin of Z sub 0. The joint Q sub 3 attached to the link 2 appears with its rotation axis Z sub 2, whose origin was located at a vertical distance L sub 1 from the origin of Z sub 1. The joint Q sub 4 of the link 3 appears with its rotation axis Z sub 3, whose origin was located at the horizontal distance L sub 3 from the origin of Z sub 2. The joint Q sub 5 of the link 4 appears with its rotation axis Z sub 4, whose origin was located at the horizontal distance L sub 4 from the origin of Z sub 3. And finally, the joint Q sub 6 of the link 5 appears with its rotation axis Z sub 5, whose origin was located at the horizontal distance L sub 5 from the origin of Z sub 4. Last reference origin is named as the robot wrist, due that it is the place where the end effector is assembled. Now, missing X and Y axes of previously mentioned origins are arbitrarily defined instead of the David-Hartenberg convention to complete the coordinate systems that are associated to the kinematics of this manipulator. Then I show the first reference frame named as the base coordinate system, where X sub 0 points in the lateral direction of this robot or outside the screen, and Y sub 0 points in the longitudinal direction of robot or to the screen's right side. Second reference frame is posteriorly shown with X sub 1 and Y sub 1 arbitrarily defined, but by respecting the right-hand rule. Pose of second reference frame with respect to the base coordinate system can be determined through the following homogeneous transformation matrix A from 0 to 1, which it is obtained from trigonometrical identities. Similar to second one, the third coordinate system is specified due that rotation axes of involved joints are parallel, and the following transformation matrix A from 1 to 2 gives the pose of the third frame with respect to the second one. Then I specify the fourth reference frame whose pose with respect to the preceding third frame is given by the following transformation matrix A from 2 to 3. Afterwards, I show the fifth reference frame whose pose with respect to the preceding fourth coordinate system is described by the transformation matrix A from 3 to 4. And finally, the sixth reference frame whose pose with respect to the preceding coordinate system is described by the transformation matrix A from 4 to 5. This frame is named as the wrist coordinate system. Regarding end effector configuration, final or gripper coordinate system is placed in the most of the cases with the same orientation of wrist coordinate system, it for simplicity when kinematic equations are computed. Then we assume here that gripped coordinate system is displaced only a distance L succeeds along z-axis of the preceding wrist frame, and thus the pose of end effector with respect to the wrist is described by the following last transformation matrix A from 5 to 6. Now we can describe the pose of end effector along the base coordinate system by solely multiplying all previous defined transformation matrices from A0 to 1 until A5 to 6. It generates the transformation matrix A0 to 6, which represents the final pose of robot's end effector from the basis. Next, I am going to show the use of the previous matrices through MATLAB and several functions developed by robotic researchers on it. So, I built the transformation matrices A0 to 1. A1 to 2, A2 to 3, A3 to 4, A4 to 5, and A5 to 6, and then the pose of an effector from the base frame would be defined by this transformation matrix. When all rotation angles are 0, the robot has the configuration of home position as this figure shows. Blue frame is the fixed base coordinate system. Red frames correspond to mobile coordinate system placed in each robot's link, and z-axes indicate the direction of their revolute joints. Another example is done by setting up these angles at the robot. Then we have the following configuration for robot frames, and the system acquired this pose. This is a short simulation that shows the evolution of robot frames while it is submitted to track a rounded rectangle-shaped trajectory in the workspace. Previous video post in my channel shows this simulation in Solid Edge. Finally, L success distance has been defined, in this case equal to 100 mm to involve the position of an effector. Now, inverse kinematics is the opposite case of previous forward kinematics. Here, it is fundamental to know the position and orientation of an effector to then calculate the rotation angle of each joint. So, in order to determine the inverse kinematics of this robot, firstly, pose of an effector is assigned noun and described by the following transformation matrix A0 to 6. Then, the pose of the wrist A0 to 5 can be represented as second matrix exhibits. In the third step, theta sub 1 is obtained from previous matrices as follows. Theta sub 1 allows to posteriorly propose the following equations to obtain theta sub 3. And theta sub 3 is used to obtain a mathematical expression for theta sub 2 as follows. In the sixth step, theta sub 4 is calculated in function of known angles theta sub 1, theta sub 2, and theta sub 3 as follows below. In the seventh step, theta sub 5 is also calculated from previous known angles as next equation shows. And finally, theta sub 6 is similarly computed in 8th step by following last equations. So, as an example for inverse kinematics, the robot's n effector has been placed in a pose defined by these angles, which generate the following transformation matrix A0 to 6. A MATLAB function has been created with previous equation programmed on it. This function takes the resulting matrix and returns the rotation angles in the joint space of this robot. The function gives the same used angles, therefore equations of inverse kinematics are valid. This is a short simulation developed on MSC Advanced View software, where ABB robot is commanded to track a spiral-shaped trajectory along z-axis as left figure shows. Thus, the robot is moving to up and down, while it makes a horizontal circumference by remaining the pose of an effector at the y-axis direction. Then, as final recommendations, we have first, kinematic analysis in this video is only a fundamental stage for this kind of systems. Another more advanced application, such as pick and place executions, will require a dynamic analysis and control system design. Second, for an efficient tracking of reference trajectories, a previous dexterity analysis must be considered to know the workspace zones where robot works better. And finally, inverse kinematic equation was obtained from successive screw displacement method previously used as another representation in the forward kinematics. In general, I would recommend this method for solving the kinematic problem on whichever manipulator robot.